good afternoon, good morning, good evening. So we are starting now our traditional IEEE Security System Society Rio Grande do Sul Talks 2020. So Maria Mushtaq received her PhD in Information Security from the University of South Brittany in France in 2019. She was awarded the French Regional Scholarship for her PhD. Currently, she's working as a CNRS postdoctoral research at LIRM in Montpellier, University of Montpellier, France, and the Excellence Postdoc Grant. She possesses expertise in microarchitectural vulnerability assessment and design and development of runtime mitigation solutions against side and covert channel information leakage in modern computing systems. Her research interests mainly focus on cryptanalysis, constructing and validating software security components, and constructing OS-based security primitives against various hardware vulnerabilities. She's currently involved in various national and international projects and has co-authored several peer-reviewed publications in international conferences and journals. She holds master and baccalaureate degrees in computer science. So thank you very much, Maria, to accept our invitation. And now I give the floor to you to start your presentation. So thank you very much. So you can start.
Thank you very much, Ricardo, for a nice introduction. And thank you very much for inviting me today to present my work. So hello, everyone. So a brief introduction about me. Ricardo has already gave some. I am Maria Mushtaq, a CNRS postdoc researcher at Montpellier in France. And I have also done my PhD from France in information security. So shortly, my research interests lie in side channel analysis and construction and validation of software security components. So in today's presentation of around 49 to 50 minutes, we are going to talk about microarchitectural vulnerabilities, their assessment, and mitigation mechanisms. So I think let's start from here, from the outline. So today we are going to talk about information security perspective at large, the problem statement in the information security, and then I'm going to talk about two frameworks which I have proposed in my work. One is the detection framework and the other is the mitigation framework. Toward the last of the presentation, we would like to talk about the conclusions and the future perspective, where security is going and what should be done. So let's start with our start of the outline, information security perspective. So, looking at this slide, actually cybersecurity is a term which encompasses a very large domain and comprises of many other aspects. So a general perspective about security is that it is related to web security or cryptography only. But actually, it is a very large domain with a very widespread application. So in every computing system, cybersecurity holds a very important agenda. We can talk that it is spread to network security, operating system, application security. We talk about digital forensics. We talk about IoT security, malware detection or analysis, and so on and so forth. There is a long list for that. And when we see its large spread, it is appropriate to assess vulnerabilities in the computing system. So let's see a bit of the introduction a little more. So security is a shared concern by many application domains in the modern era, actually. All the critical infrastructure, like we talk about health sector, we talk about e-governance, we talk about the financial sector, every critical infrastructure requires security today. So behind all these services, there lies a computing infrastructure that make these services either secure or insecure. So let's have a look at that computing infrastructure that can make these services vulnerable. As you can see on the right side of the slide, there is a conventional computing stack which is very successful due to one reason. that it allows the evolution of software layers from the hardware layers independently. But if we talk about the security perspective, the problem arises when we see that all the layers, either we talk about the software or we talk about the hardware, they are leaking information. So the problem is that information leakage is possible even under the safe software, even if we are using encryption algorithms. But this is not happening due to the encryption. It is happening because the underlying hardware is vulnerable. The way we are computing software on the hardware, that is the actual problem. So let's have a look at how a side channel or how information leakage actually happens. So this is a main channel information. In this slide you can see where we have let's say a cryptographic operation happening on the commodity hardware, where we have a plain text and the key as input. We do the encryption process and we have a ciphertext as the output. So this is the normal procedure in the main flow. But while doing so on the commodity hardware, we have several side channel information that is relayed. That can be data or instruction timing, power, data instruction access, and many more. So having this side channel information in the first place is not a problem. But using this side channel information to extract the main channel information is the real problem, and this is how the information is leaked. So let's talk about my perspective on encryption. There was a time when a security society was saying that okay, use of encryption algorithms is maybe a problem, maybe its execution on hardware is the problem, so we have to fix actually the encryption algorithm. But actually that's not a problem. There is nothing wrong with the encryption. I will give you one example here of Seagate technology paper which tried to do a brute force attack on AES 128-bit key, which is used frequently, and it is considered very safe. So I will read this example for you that, for example, if still there are 7 billion people on the planet, and I think if we count Pakistan and Brazil in it, we will make half of it. Anyway, so if there are 7 billion people on the planet and every person owns 10 computers, and these computers can test 1 billion key combinations per second, and the key can be retrieved after testing 50% of the possibilities. Still, if we assume all this, then the Earth's population can crack one encryption key in this many years, which is very long. So this shows that encryption is very, very strong mathematical operations. But what happens that when we tried a simple cache side channel attack, for example, flush and reload attack on Intel's i7 machine, it was capable to recover the AES secret key in just 28 milliseconds. I repeat here, in just 28 milliseconds. So I let this information sink in, and we see that today the problem of security is enormous, and this is where we have to take it seriously. So let's have a look at what is an abstract view of the shared memory architecture, which makes a lot of information leakage. So if we look at it, there are different compartmentalization of it. For example, there is a part on the computational side where we have logical CPUs scheduled on the physical cores, and one side is the storage perspective, where we have different levels of caches which are shared between CPUs related to the same core. And then we have the last level cache, which is inclusive in nature, which is shared between all the logical CPUs. So this property of sharing in the hardware architectures or inclusivity is leading to a lot of information leakage. So now let me elaborate that how two different processes, if they are running on a shared hardware, what they are doing and how a side channel is built or how information leakage is happening. So here in this slide, you can see the leakage through the shared memory, where we have two processes. Process 1 is a malicious process, and process 2 is doing encryption, as I explained earlier. So if we look that a malicious process wants to access information directly of process 2, the system software or the operating system is designed in such a way that it does not allow a direct access of a malicious process to the encryption process. Okay. However, both these processes are utilizing the shared hardware resources. In this case, it is last level cache, which is inclusive in nature. So the malicious process can get to know the side channel information like memory access pattern or timing in forms of cache hits, cache misses. It can retrieve the secret information of the process too. So having said that, simple side channel information like memory access pattern, timing information is the real problem of leakage here. So now gone are those days when we were saying that the cache side channel attacks or the storage perspective attacks are all believing in encryption algorithms. Now there are also attacks at the computational part, which has proven to be more sophisticated, and they have shown us multiple security breaches. For example, maybe you have listened about Spectre and Meltdown vulnerabilities, which use the performance features which were very hard earned in last 20 years. They use those performance features like out of order execution or the branch prediction unit to launch an attack on the shared hardware. So there are attacks which are crypto based, and then there are attacks which are more sophisticated than that, and all the layers, this is how that all the layers, the storage or the computational part, it is leaking from the logical CPUs to the cores, to the caches, to the memories, to the network interconnects. Now I would like to present Intel x86 architecture, which is not the only one, but the biggest casualty of security vulnerabilities, which is our threat model here. As we can see here, that there are many cache side channel attacks and covert channel attacks which are happening on the computational perspective or on the storage perspective. Some famous attacks are Spectre, Meltdown, Prime and Probe, Flush and Reload, Flush and Flush, and many other attacks. List is very, very long. And there are many unknown vulnerabilities which are going to come in future. So let's discuss that what makes these cache side channel attacks very interesting for us. Cache side channel attacks actually are non-invasive in nature, which makes them very important here or significant. They are passive. They are very high resolution attacks. Cache side channel attacks do not respect any privileges. In state of the art, you will find attacks which are cross CPU, which are cross core, which are cross VM. And if we look at the helicopter view of these attacks, it is actually simply three-pronged. In first stage, the attacker manipulates the cache to a known state, and then it goes into the wait state and it lets the victim to execute. And once the victim has finished its execution, it does the observation and examine that what has changed. So this is all the procedure of a cache side channel attacks, and that is why they are very hard to detect, because they are actually the part of the hardware design. So now, out of all these attacks, I can give you a brief understanding of one attack so that we can linger on over discussions and results. So maybe you will, that point, you will know that how this, the philosophy of this attack works. So in the first phase of the attack, the attacker address space primes the cache by its own data. As the second step, it goes into the wait state and it lets the victim to execute. So victim accesses different addresses at the shared memory. And at the third step, the attacker probes the cache and it sees that by simple timing information that what has changed related to or in comparison to what he filled. So a simple timing information in form of cache hit or cache miss can actually reveal that what has been generated by the victim and which specific addresses the victim is interested in. And this is how a secret key of a victim is revealed by a simple timing monitoring. So before we start about talking that how to deal with side channel attacks, let's talk that what is already available from last 10 to 20 years in terms of state of the art on defenses on cache side channel attacks. So talking about the defense approaches, there are hardware approaches and there are software approaches. In hardware, we have partitioning based approaches, we have randomization based approaches. Then in software, we have different scheduling based approaches or obfuscation based approaches. But all these approaches are vulnerability specific. And if we look at the state of the art, we see a lot of things missing. For example, mitigations are not covering a large attack vector. Mitigations are not system-wide. Mitigations are performance-heavy, and at this point, we don't want to lose a lot on performance because these are the hard-earned performance benefits which we got in last 20 years. So we want to achieve security, but not on the cost of a lot of performance. So let's talk today that what can be the way forward for this problem statement I have explained you here. So I'm going to explain some facts here, and then we are going to talk about that what can be the way forward. So first of all, the attack surface is not completely known yet. It is rather expanding from the storage part to the computational part to the network interconnects. If we look at the computing stack, all the layers are leaking information, and the intended security efforts like Intel XGX or ARM's trust zone, they are still vulnerable to cache side channel attacks. So there is a complete paradigm shift which is going towards security. So on the one hand, security has become a first-class design constraint, and on the second hand, there is a prevailing consensus that security must be made a part of all the layers in the computing stack. So let's see that what can be done related to this problem. So first solution which comes to our mind is secure by design solutions, where attacks are not feasible in the first place. For example, we have to design systems in which we should have bug-free software applications. We should have operating system or hypervisor which provides a complete isolation. We secure all the system components. And then we redesign a non-leaky hardware. But here the problem comes that doing all these things all together is not possible today. This idea seems to be a solution of future. But what can be done to contain the attacks right now and today? So I propose a second idea, which is secure at runtime, where the attacks can happen, but their impact and value is contained at the runtime. So I argument that unless we have solutions like secure by design solutions, we have to work on secure at runtime solution to stay or to limit in our boundaries in the current hardware architecture, and we try to contain the impact of this attack. So in the absence of secure by design solutions, my work argues that there is a need to provide a need-based mitigation mechanism which can help the computing base from these threats. So I have proposed 3 different modules to do that. First is the attack vector development and analysis, and then I have provided 2 different frameworks for runtime detection of these attacks and runtime mitigation under different use case cache side channel attacks. So this was a brief perspective on the problem statement of information security and a large perspective toward that. Let's talk about the detection framework, which is the one framework which is proposed by us. And let's talk how does this work and what is needed to do here. First, we are going to talk about the attack vector development and analysis here. So if we look at the victim perspective, when cache side channel attacks are happening, different victim processes, which are represented here in green and the attacker in orange, they are accessing the cache and they are polluting different cache addresses. So what makes them analyzable is their behavior, because when they are executing, they are actually changing the cache behavior, or they are altering altogether the cache behavior. So what are the behaviors which we can note are, for example, access time, access order or pattern, cache misses, cache hits. So we have performed a number of such behavioral analysis on the cache, and we have compared that what happens when we are under no attack and when we are under attack. So now we need something to analyze these behaviors. For that, we have used different performance counters, software performance counters and hardware performance counters as features to different cache levels, as you can see here. And we have also proposed to work on system-wide counters, which contain the performance optimized counters on performance optimization features, which can not only cover the storage perspective attacks, but also they will be intelligent enough to cover the computational attacks. So we experimented in by all these 15 events, and we selected them according to the attack behavior. Now we are interested to see that how these performance counters look like. For example, I have provided here the execution traces on prime and probe attack under no load conditions, where the load on the system is just the attacker and the victim. Here you can see I have shown 4 different counters: L1 data cache misses, L1 total cache excesses, L3 total cache misses, and total cycles. The red distribution shows the attacking behavior, and the green distribution shows the no attack behavior. So here we were very intrigued to know that performance counters can so beautifully do the behavioral analysis for us. We can see in all the cases that the attacking behavior is quite distinguishable from the no attacking behavior. For example, for L3 total cache excesses, if we somehow here do a simple threshold mechanism and we say that if we are going above than this ratio, then we are going toward attack, and if we are below this, we are under no attack and there is no threat in the system. Okay, now let's talk about how the runtime detection mechanism actually works. The situation gets very interesting here, and these results are very interesting to present. We can see the performance counters when there are multiple CPU and memory intensive benchmarks are working, and now the system is not in isolated condition where only the victim and the attacker is there. We have introduced noise, which is the realistic scenario actually. And then we have introduced multiple attacks at the runtime. Okay, so here you can see that there is no attack behavior, and then we have multiple attacks here. We have tried to do prime and probe attack, flush and reload, and their different variants with full secret key and half secret key. Now, interestingly, the results here show that only maybe one performance counters is able to distinguish a bit about the attack and no attack behavior. But when we plotted all these attacks all together, we were seeing that the green bars are not distinguishable with the other attack behaviors. So our problem of data distribution is quite complex, and a single ad hoc threshold-based mechanism cannot work here. So this was very interesting to analyze this type of results. And here we saw that our friend machine learning can help here, which can analyze these behaviors at the runtime, and we can train all these mixed distributions to machine learning models, and it can do the job for us, like binary classification, to detect an attack or no attack. So this is how the problem statement got more complex, and we started to use machine learning. So coming toward the machine learning models, many classical models can do the job, like linear models, non-linear models, but the selection of the machine learning model in our case was dependent on the attack behavior, number one, and then we were depending on different parameters. Like we wanted to achieve high detection accuracy, high detection speed, and we wanted the machine learning model to have a smaller footprint. We wanted a low implementation complexity for these models. And we also wanted a low performance overhead in terms of detection mechanism. So this is how we experimented all these 12 models, and we saw that which models suit the best for our attack cases. Now here, this figure basically sums up all the detection mechanism. So in detection mechanism, it is happening in two steps. So in the first step, we are doing the real-time, there are real-time processes, and we are doing attack vector development and its analysis by using hardware performance counters and software performance counters for the real hardware. So when this data, we are collecting it at different sampling granularity. When we receive this data, it is then passed to our second module, which is the detection module, and it does the runtime binary classification for the attack and no attack. One very interesting thing I want to tell you here, that when we were doing the isolated load conditions and the attacking and no attacking behavior was quite distinguishable, we were also trying to look into different machine learning models separately. But when the problem started to be complex and undistinguishable, we also not only worked on single attack detection, but we also worked by combining the machine learning models in our ensemble module of detection, which does the majority voting for classification of attacks, to be really sure that the process we are detecting is vulnerable. Now, one important factor when our detection methodology was built, and we had a proof of concept, we have to validate it on different use case cache side channel attacks, and they should be enough to do this testing. So for that purpose, we have reproduced different attacks from the storage perspective and from the computational perspective. As you can see, we reproduced in total 9 attacks with a different perspective of storage and computation. We took different crypto systems into account, and attacks which are not based on the crypto systems, we have tried on different OpenSSL versions and not for the computational attacks. And then they had different variants for full key message, half key message, full message exploitation. So we actually developed a large pool to test our proof of concept of detection mechanism. So now I'm going to give you one effective result out of many on the detection framework, and we are going to talk about this result in detail. So as I have shown you that we have used different machine learning models, and we have introduced different load conditions, zero load or no load, medium load or average load, or high load or full load conditions we have introduced. We can see that all these models altogether are providing a very nice accuracy by just using simple classical linear or non-linear models. We didn't go till now into deep learning or models which are neural network based. So we can see by just these simple models, we were able to achieve a very high accuracy for the detection of our results. And we can see that at a very low sampling granularity, which is 0.9% here, it means that I would like to explain here that flush and reload attack on RSA has a secret key of 1024 bits in total. So it means that before the 10 bits were computed, we were able to detect the attack at fine granularity. And then we were achieving negligible distribution of error in the form of false positives and false negatives. And the last factor, which is our design metric, was overhead, which is dependent on the sampling frequency and the overhead of machine learning model itself. And we saw that all these models performed really nicely for detection of flush and reload attack on RSA crypto system. They differ a bit, but I think all of them were showing very nice accuracies and low overhead. Okay, so this was all the perspective for the attacks which are crypto-based or which are developing on the storage perspective. Now let's see that what is happening on the computational perspective. So there was a big breakthrough in 2018 where multiple security breaches were introduced. And international media was covering this news all around. We saw BBC, CNN, Fox News, all of them talking about these vulnerabilities. And the authors who found this bug, they call these Spectre and Meltdown vulnerabilities. So this was a big talk in the town of security society, and everyone from 2018 is seeing different variants of these attacks, and this is still the talk of the town. So let's see what are these attacks doing. So I have explained here that both the attacks are exploiting performance enhancement techniques, and both the attacks are two-phased. So if we see the meltdown attack, it has first phase, which exploits the out-of-order execution and uses cache side channel attack in the second phase to extract the victim's information. And if we look at the Spectre vulnerabilities, in the first phase, it exploits the branch prediction unit by the speculative execution, and then it uses cache side channel attack in the second phase to retrieve the information of the victim. Now let's go a little bit deeper into these attacks. So we can see that in the meltdown attack, there is a deliberate race condition which is happening here between the out-of-order execution and excess permission checks. So when the permission checks is discarded for some wrong process or the attacker process, till that time, when it is interrupted, the execution results are discarded right at the moment. But the results in the caches are still there, and a simple timing-based attack like flush and reload or prime and probe can work there and retrieve the victim's information. And if we talk about the Spectre attack, it also uses the vulnerability of speculative execution of branches. They are actually designed in modern computers for performance boost up in the performance optimizations, but it mistrains branch prediction to convince CPU to speculatively execute code that actually should not be executed until the time the system confirms that this instruction should be discarded. And it is discarded, but still the data remains in the cache, and the simple timing flush and reload attack was able to recover that data. Okay, so let's see very interesting system-wide counters, the software performance counters, which we have used, for example, for meltdown and Spectre attack. So it is very interesting to see these results. I am showing you here the total instructions and the page fault results. And we have a meltdown attack, we have benchmark processes running, and we have one web browser application which is doing some procedures. Okay, so now we can see that the meltdown attack here is producing very less total instructions. But if we look at the page faults, we see that for this very less number of total instructions, the meltdown attack is producing this big number of page faults. And then we compared the normal processes which have more total instructions, but they were producing very less page faults. So when we compared this attack, the normal procedure with the abnormal one, we saw that, okay, for here something wrong is happening actually. And if we look the same results for total instructions and branch instructions mispredicted for SPECT vulnerability, we also saw something wrong happening here, that the total instructions of SPECT attack are this less, and then it was able to do a lot of branch instructions mispredicted. So when we compared these results with one of our master students, we saw that the performance counters, either we talk about software or hardware, they are providing a very nice behavioral information, and they are a nice tool to indicate the attacking and the no attacking behavior. So when we observed these behaviors, we also tried to do detection of attacks, SPECT and Meltdown. I'm going to today show you one result here for the Meltdown detection. And we can see that the three models we used for Meltdown attack under different load conditions, all of them are providing accuracy above 98% for the detection. The speed of these attacks, because they are not a crypto attack, so the speed is uniform, and at 10 microseconds as a fine grain sampling, we were able to detect this attack with a very, you can see all over, with a very negligible distribution of error of false negatives and false negative positives, and the overhead is still manageable, which we are achieving. So this is all about detection mechanism, and the results I have shown you here, they show very encouraging results that we are able to detect the attacks at the storage perspective and at the computational perspective very efficiently, and detection as a first line of defense can be a nice direction. Now, let's talk about the second framework, which is our mitigation framework. Let's see that after detection, are we able to mitigate the attack at the runtime or not? And for that, we are going to talk about our last module, which is the runtime mitigation. So now attacks are happening in any simultaneous fashion. So we have to do their detection and mitigation. So just to give you an abstract view that where actually our detection is mechanism is happening and where our mitigation mechanism is happening. And then I'm going into detail of the methodology. So our detection framework is actually working in the user space, and our mitigation framework is working in the kernel space. And you can see that these two spaces have a large wall inside. So there should be a way to do a communication from the user space to the kernel space. So once our attack is detected, we are using different methods to communicate to our mitigation framework to take mitigative action. So here, this figure actually, this representation basically sums up all the three modules, where we are getting the real-time data from the hardware, which is then passed to the user space, where our second module, the detection framework, is working, and which is doing the behavioral analysis and runtime classification for attack behavior. And once a vulnerability is detected, it is then passed to our third module, which is working in the kernel space, is named as mitigation module. So what does it do? That it evaluates the vulnerable process as a trusted or a non-trusted process. So if the process is trusted, we resume the trusted execution, and if it is not trusted, we take the mitigative action here. And then we resume the trusted execution again. So if we look at the results of the mitigation mechanism, I'm going to present you one result here of detection-based mitigation of flush and reload attack on RSA. So what you will see here is different timing representations in this figure, and in the blue bars you will see the RSA crypto system running alone and the RSA running with the attacker process, the flush and reload attack. And the green distributions here show actually the timing information of our proposed detection-based mitigation mechanism. So here we would like to tell that the detection-based mitigation mechanism was able to detect and mitigate the attack in less than 2% of the attack completion, which means that toward around 20 bits out of 1024 bits, we were able to detect and mitigate the attack at the runtime, which is far below the 50% completion of the attack. Because the crypto community and the security community has a consensus that if the attacker is able to achieve the 50% of the secret key, it is able to do reverse engineering to build the other 50% of the key. But our mechanism was efficient enough to detect and mitigate the attack even below and far below the 50% of attack completion. Okay, so this was all about the detection to mitigation and seeing different attacks and from the storage perspective and from the computational perspective. So now let's have a look at the last part of our presentation, which is about conclusions and the future perspectives. So here, let's have a look at conclusions at large. We can see that side channel information leakage is powerful and attack surface is expanding day by day. There are known vulnerabilities, there are unknown vulnerabilities which are going to come. I am forcing this point again and again that there are attacks in all our computing stack. So either we talk about software, we talk about hardware, we talk about shared hardware architecture or not. All and every system today is leaking information. So need-based protection has the potential to contain side channel attacks, both the computational and the storage perspective. And then they are able to retain the hard-earned performance benefits. We are not losing a lot on performance. So detection seems to be promising, and it can serve as the first line of defense in the absence of secure by design solutions. And toward the last and very interesting point I want to emphasize is that machine learning can help improving security. Though we explored very basic models of machine learning, but I really believe that use of specialized machine learning models and deep learning models can help us make automated vulnerability assessment mechanisms or more sophisticated detection mechanisms for future to make systems more reliable. So now let's talk about the future perspectives. So let's see, even after these solutions, where are we going and what is going to happen? So, and what can be the way forward? So the prevailing attack surface is expanding day by day. There is a continuous race condition between the attackers and the designers here. If we look at the attack surface, there are attacks at the software side and there are attacks at the hardware side. The attacks are internal, they can be external. And then if we look at the information retrieval attacks in state of the art, we see that there are software attacks focusing software or hardware. And then there are hardware attacks which are focusing hardware or software. And all these attacks are focusing on the protecting or targeting the protected software or the trusted computing base itself. So here we understood that the prevailing attack surface and the challenge of information security is very strong. And this challenge is enormous, and we have to deal with this problem. There are radical design changes which are required in the computing stack to make or to go toward more sustainable solutions. So here we are going to talk that, okay, we understood what is the problem. Now, what can be different directions to look into? So I have given shortly 3 perspectives in which we can work on. So security has become a first-class design constraint. So this is the time where we say that security should be considered as a prime time component in the computing stack. Gone are those days where performance was only the important thing in our computing stack. So we have to give more importance to security in the future systems. So modern security challenges are emerging from the way we are computing today. So there are radical design changes which are required at the both hardware and software level to cope up this security challenge. And lastly, unfortunately, there is no computing platform which is secure today. And the attack surface is going to expand even further in the future. So there are tools which are required to contain the existing vulnerabilities, and the future systems should be made more predictable. We don't want to go into a future where we don't know where the security is going and how the security should be designed for the future systems. Whatever technology we are choosing, wherever our architecture or hardware efforts are going, we have to look, or we have to give security its primary importance so that the future systems are not totally unknown to us. So here are some relevant publications of my work, which I have presented here in terms of conference and journal papers. I believe in 40 to 45 minutes, not everyone can understand all the domain. And if someone is interested to look into side channel analysis, their detection and their mitigation techniques, so this is what we are doing, and what I'm presenting today is actually from these papers. So you can go into them, you can look into them if you are interested in this domain. And now here is our team who had been and who is still backing up my work. And so basically we belong from EDAC Computing Lab at LIM, University of Montpellier in France. And you can go into our profiles, you can look what kind of work we are doing, and you can contact us. We are all open to work collaborations, to master's and PhD students or different researchers. If they want to work with us, we are quite welcoming in that sense. So here I would like to thank you for listening and bearing me for around 46 minutes, and I'm open to our discussion. And if someone has questions more than this 10 minutes or 20 minutes discussion, he or she can contact me. I'm open to discuss more and to chat with you about what I have presented to you today. Thank you very much. I give the floor back to Ricardo now.
Thank you very much, Maria.
Welcome.
Very nice, interesting talk. So we are open for questions. So please do your question as soon as possible. So we have one question from Maria Iqbal from Zikria University. So her question is, how do security capability, maturity, and risk level correlate?
How does security?
Capability, maturity.
So she wants to say that how security can work with capability and maturity?
Yeah, how they are correlated.
So I can have my opinion about it, that security is still from last 10 to 12 years. It is emerging, and it is the efforts are going on to be more capable and to be more mature. But this is a thing in process, as I explained earlier, that right now we don't have the mature solutions or very capable solutions to cope up all this security challenge. But for future, these are the perspectives where we need to go to make it more capable domain and more mature domain.
Okay, thank you. So you talk about that we need some radical changes in both software and hardware levels to improve security. Can you talk a little bit more about that? So which kind of hardware, which changes in hardware or software are important to improve security?
Okay, so first of all, I have a perspective toward this, that okay, the problem is emerging from the software execution on the real hardware. So the problem is emerging that all the computing stack, either we talk from software to the hardware, is leaking. So I also said that there are radical design changes which are required in software and hardware. So I would like to say that first of all, we should need to work at the software level on automated attack assessments. We need to find a way, or we need to develop different matrices where we can use different machine learning model or different traces execution platforms where we can actually detect the attacks at the runtime, or we can actually analyze that where in the hardware or which components are actually causing these leakages. Number two, I want to work on a secure operating system and hypervisor. I argument this idea that, for example, the attacks like Spectre and Meltdown are happening because OS was given these permissions to actually schedule these processes on our cores. So mainly the operating system or the hypervisor layer should work more or revise more the T-based implementations or environments, and we should work on more isolation-based approaches, and we should be able to make them secure from such sophisticated threats. Then later on, toward the hardware, there can be different solutions on which we can work. But right now, what we see that the problem is emerging from the extra architectural state. As you have seen, the attacks on storage are based on the information which is still in the cache, and the timing information can reveal it. If we go toward the computational perspective, the information is not directly related to the cache, but somehow the discarded information is still placed in the cache, and this extra microarchitectural state needs to be redeclared, and this needs to be worked on in our instruction set architecture to cope up this security challenge.
So we have a question here. Thank you, Maria. I have a question from Matheus Leme from Federal University of Rio Grande do Sul. Thank you for the excellent presentation. Do you intend to perform a power analysis attack?
Till now, I'm a person from the software component side. I have not touched the hardware attacks till now, like power analysis or different attacks of this nature. But I still believe that the behavioral analysis, even on those attacks at the hardware level, can also reveal a lot of interesting information. But because I have not experimented anything, I will not be sure to say, but I believe in this, that this way, as a first line of defense, detection or this type of mitigation should work.
Okay, thank you. Welcome. So a question by Madiha Zaidi from Hamdard University in Karachi. So your work is pretty detailed, but since currently we don't have any mature systems, how long do you think we will be able to create such solutions? Have you guys made any such prototype?
So actually, we had made prototypes. All the experimental setups I'm showing you here were working, but the type of efforts which I'm talking about for the future, there are many labs which are working on these ideas in US. I know University of California is working on this idea. For example, if we talk about France, it's LEM itself, Labstick. In Iran, there is a lab, ERISA. They are working on automated vulnerability assessment. So there are different efforts going on towards software and hardware. You know, the problem to deal with this challenge is quite huge. We have the software side, we have the hardware side. If we are able to cover one challenge, the other vulnerability comes and disrupts everything. So there is a complete rehauling which is happening in different labs, I believe, and different research units in the world who are working on these challenges slow by slow. And I hope soon, in next years, we will be able to see these changes actually. And if she's talking about some prototype or some already some efforts toward it, RISC-V is a nice initiative, and it is quite transparent. They can use that. They are still a little vulnerable to side channels, but it is still, I can say, it is better than all the existing architectures.
Thank you, Maria. So another question by Mateus Leme. Do you have an idea of the impact of sampling frequency during trace acquisition in relation to the vulnerability results during cache side channel attack?
So actually, sampling frequency is very related to the performance overhead. So we tried in our results, I have not shown you the details, but my papers can show this, that we have done the sampling frequency at different granularities. So now, if you are doing the sampling frequency and you at a very fine grain level, and you want to detect the attack at a very high speed, then you pay a bit of the performance cost in terms of sampling at a very high frequency and counting the events very fast. And then you can go for a coarse grain sampling rate, where you can choose like, for example, I did sampling at 10 samples. They can do at 50 or 100, but this will it will have two benefits. Number one is that you will be sure, like you will give 5 or 10 samples in between to be sure about the attack. And number two, it will reduce the performance overhead to a greater extent, to almost half what I'm presenting.
Thank you. Now I have a question from Juan Carlos Sanchi. So Juan Carlos is from National Polytechnic Institute in Mexico City. Mm-hmm. So what do you think is more adequate for good implementation of secure hardware? Full custom chip or FPGA implementation?
That is a question a bit out of my domain, but I would say we have to experiment toward it. I'm not an expert to comment on FPGAs. I have never worked in them, so I think I will not comment toward that.
Maybe I can add that. I think
maybe someone from a hardware perspective or expertise having in hardware can really answer this question.
I think that in full custom chip we can do more designs, implementations to cope with security. So another question from Saad Maliki. So thanks for your talk. It was very useful. There is always some problem in each domain. Everyone belonging to that domain wants to work on. Do you have any such problem you would like to work on in future? So I think is missing part of the question, but.
So the question is that there are different domains on which people are working, and then?
There are always some problem in each domain, everyone belonging to that domain wants to work on. Do you have any such problem you would like to work on in the future? So I think it's something that when you are working on domain, there is also some things that are related, that are in a neighboring domain, and so if you have some things that you want to address in the future.
Okay, thank you, Saad, for your question. I would like to answer it the way, like machine learning, for example, was a domain which was at that time when I started to work in it, it was quite new in security. There were some researchers who were working around it, and I was one of them. So it is a very interesting domain which I see to be worked on in security. And I believe that if we work on more specialized form of AI and machine learning models or deep learning models, I think we can make the detection or mitigation mechanisms more robust. And I believe that we should go in more detail of machine learning and to deploy more sophisticated mechanisms. So right now I see, related to my work, I see this domain as a neighboring domain which can be really helpful.
Okay, yeah, the subject is very interesting. We could start doing a debate here for several hours now.
Yeah, that is why I told that maybe the time will finish. People can contact me by email or.
Yes, for sure. Yeah, because I think there is still a large space to work on to improve security, mainly at the hardware level. No?
Yes.
Yeah. Okay, so thank you very much, Maria. It was a very nice and interesting talk. So I hope to see you soon in face-to-face.
Yeah, I hope this COVID situation finishes.
Yeah, I hope that. So now I would like to invite all you for the. If you have not yet subscribed to the YouTube channel of our chapter, please do it to receive more information about future activities. Thank you very much. Thank you, Maria. Thank you, all attendees, and see you next week. Bye-bye.
See
Have a
you.
nice weekend.
Thank you all. Have a nice weekend.